so that I can post them up. I tried this last semester. I posted them to YouTube, and that seemed to work fairly well. There's a lot of material, so folks like to be able to go back and review what we talked about. I've also posted the presentation for tonight. It has been posted to Blackboard. So make sure in this class you check with Blackboard often for when I post new material. Okay, folks are still joining in. Okay, looks like most everybody's here. Okay, so I usually start these classes by going over the syllabus and kind of just a little summary of who I am, why I'm here, and what we're going to do. First of all, I apologize that this is the way we have to do this. Normally, I get up in front of a big whiteboard with a bunch of pens, and I'm able to kind of be interactive. I like to engage students and make sure everybody's on the same page before we race ahead to the next topic. It's a lot more difficult to do in this environment, but this is what we have, and we got to make the best of it. So this will be the way that we meet twice a week. We're going to be meeting on Tuesdays and Thursdays, 5 o'clock to 7:05, I believe. And I believe the Zoom invite that I gave you is good for the entire summer session. So just keep using the same invite. I made it a reoccurring and I ran it all the way to the end. So with that out of the way, housekeeping out of the way, let me tell you a little bit about what you're signed up for here. First of all, my name is Aaron Pratt. I am a licensed structural engineer in the state of California, Nevada, and I'm actually a civil engineer in Arizona. I have been working for the same company for just past up 25 years. So I work for a precast, pre-stress concrete company, and basically I work as a structural engineer and run a structural engineering department, and we design concrete products day in and day out. So this class, more than really any other class I teach, is pretty much what I do and have been doing for 25 years. So that's what I do, and that's who I am. Oh, I've been teaching here at Cal Poly 15, 16 years now, kind of off and on. My full-time job is working for the precast company. So this is really just a hobby. I kind of just do this for fun. And that's why I don't teach more than one class a quarter or semester or summer session, what have you. I can only handle about one because I do this in my spare time. So that's who I am. I've taught this course before, probably about a dozen times. Like I said, this is pretty much the one closest and most dear to me. I can be reached by phone at 626-962-8751, extension 6216, if you can see my screen still. You can email me at the epratt@clarkpacific.com email address. I actually would prefer if you email me to this address as opposed to the edpratt@cpp email address. I check both, but I don't check the Cal Poly one all the time. And if I get an email through the Clark Pacific, it comes up instantly. So I would prefer, or you'll get a better response if you use that email. Everybody okay so far?
Yeah, we're good.
Yeah. Yes, we're good.
Yes.
Okay, great. And I do have I keep the chat window open too. So if you don't want to try to interrupt me, you can always write something in the chat. You can tell me to slow down. You can tell me go back over that. I'm completely lost. Whatever. So you can speak up or you can chat and I will immediately respond. Okay, so continuing, I will have office hours. I'll do them the hour before this class. So that's Tuesday, Thursday from 4 o'clock to 5 o'clock. I have another Zoom invite that pretty sure I posted that to Blackboard as well. So basically what I'll do is I'll just open up Zoom and I'll just keep it open until, well, honestly, if nobody shows up by about 4:30, 4:45, then I'll take a little break before I start this lecture. But jump in on that and I'll be monitoring that if you have any questions during the course of the semester. So Tuesday to Thursday, 4 to 5 p.m. or by appointment, and just log into the Zoom and I'll be there. Next topic is the required textbooks. And I believe these are fairly important. First of all, our text for the course is Design of Reinforced Concrete, J.C. McCormick, R.H. Brown, 10th edition. Now, I know these days you have options. You have options of buying the textbook and having it in front of you, or you have the option of buying a digital version and you have it on a PDF on your laptop or what have you. You have options of renting your books, I understand these days. And so there's lots of options. But before you make your decision, oh yeah, of course, there's also the option of not buying the textbook and just trying to wing it. I don't recommend that option. This is a lot of material. I can't cover everything. I'll cover a lot of stuff, but I can't cover everything. So I don't recommend trying to wing it without the book. Of course, that's just me. Now, before you make your decision on how or if you're going to buy this book, please understand that we have one midterm and we're going to have one final. Both of those exams, just by the nature of how we do this, how we have to do this, both of those exams will be administered by the Respondus browser lockdown software. I would assume that you guys are familiar with this now if you've taken it from the last semester. If you're not familiar with this, it is a software package that you download. I put the link up on the Blackboard so you can get to it. You download that software package onto your laptop or computer, and then I load up the test on Blackboard. You go through Respondus to get to Blackboard to get to the test when you're taking the test, and what it does is it locks out everything else. So if you're using a laptop, if you're using your desktop, doesn't matter, it locks out everything else. So obviously you can't have the test on one screen and Google on the other screen so you can look up all the answers. That's the whole point of it. And it also, you have to have a webcam watching you so that we know you're not just sitting there texting your classmates asking for the answers. Because we're using Respondus, you have to think a little bit about how you want to buy your textbook. The tests will be open book, but if you've bought the digital version of it, you're not going to be able to get to it during the test. It locks everything out. So if you have the digital version of the textbook, what you're going to have to do is basically ascertain which chapters the test is going to cover and print out what you think you're going to need for the test and have it in either a bound or a 3-ring binder or something of that effect. And basically you'll just hold that up for the test and say, here's my textbook. Okay. Any questions at all about that? What if I have the book on a tablet? Yep, that's the digital version that I was talking about. So what you're going to want to do is print it out. You're going to want to print out the sections that you need. And this did come up. The last semester that I taught was mechanics and materials, which is a very rigorous class, you all will remember. And we had, I don't know, maybe a third or so of my students had bought the digital version. And so what do we do? And then that's what they would do is they would just take the PDF and print it out, or go down to Kinko's or FedEx or someplace like that and print out the portion of the book that they would need for the test. Any other questions about the textbook?
Professor, for the second one, the codes,
Yes.
is that okay if we have it on a PDF, or would you recommend us to buy that for the test too? Or rent it for the test too?
That's a good question. And Jesus, I see you've got a question as well. The code, I don't see the code being as absolutely necessary as the textbook for taking tests. I do see the code as being very, very important for understanding this class, but I don't see it being as necessary for taking the test. And two reasons. One is I'm going to let you bring in one sheet of handwritten notes. So you can copy stuff that you would need from the code to one sheet of handwritten notes. That's one way to get around that. And two, a lot of what's in the code is repeated in the textbook, because this textbook, the 10th edition, has been updated to ACI 318.14. So if you had the textbook, you kind of have what's important to you from the code. Okay, and then Jesus, would the book be a valuable reference when we're in industry? I think the answer to that question very much depends on what it is you'd like to do with your life in the simplest way. So if you see yourself doing structural design, if you see yourself going into that field, then absolutely a valuable reference, absolutely. And the ACI 318.14 also is a very valuable reference to that as well. If you see yourself going into project management or traffic design or wastewater or some other part of the immensely wide breadth of civil engineering, then it's a good reference book. It's always a good reference book, but maybe not quite as valuable to you. When I went through my courses in college, I knew I wanted to be a structural engineer, and I still have every single one of my concrete books, steel book, mechanics and materials books, and I still pull them off the shelf from time to time, and they are still valuable, yes. So hopefully that answered that question. Okay, okay, so that was the textbook. The code, I think, is going to be very valuable as well. I am going to refer to the code constantly in this class. I've written up a lot of the lectures already, and I refer to the code a lot. And so it's going to be very, very helpful to have it right there in front of you so that you can look up what I'm talking about and start getting familiar with the layout of the code. I'll tell you one thing, you guys are lucky. You guys are lucky, because I learned under the 94 code, and then we went to 99, 2002, 2005, 2009, 2012. It's the 2014, they completely reorganized the whole thing. And so all of us in the industry are struggling, really struggling to understand this. But it actually makes a lot more sense the way that they reorganized it. So like I said, you guys are lucky. You're going to learn it in the better way, the more reorganized way that actually makes a lot more sense than the way that we all learned it. Okay, so that's what I have for that. I don't understand why this one person keeps trying to get in here. Hmm. Anyway, okay, we shall move forward. So this is a 10-week course in the summer session. We're going to kind of cram a whole 15-week semester into a 10-week course. And to be honest with you guys, this area down here in weeks 7 through 10, this is probably going to change. This is evolving a little bit because I'm still putting together the lecture notes of going from in classroom to the virtual environment. Actually, on my end, requires quite a bit, a very substantial amount of pre-work that has to be done before we can do these lectures. So I'm down in here now and I'm making my way down, but these might change. The midterm is not going to change. The midterm will be July 2nd. And then this I put in here July 30th as like a catch-up day, because I'm not sure if we're going to hit every single one of these lectures and finish in the 2 hours. So I kind of worked in a flex day, if you will, to get caught up in case we get jammed up just before the midterm. Okay, so these are the topics that we're going to be covering. We are going to be doing homework, one homework assignment every week. I'm going to work on it this weekend, and I'm going to give you the homework assignment on Tuesday, and then it will be due every following Tuesday. So every Tuesday, I give you a new assignment, and you have a week to complete. Let's see, anything else?
Is there a certain format you want the homework to be in?
Yes, there is, and I'll talk about that in a second. Thank you very much. Yeah, I'm kind of jumping around a little bit, but I'll talk about that in a sec. But the homeworks, I will give the homework assignments on Blackboard. I'll make an announcement of what each homework assignment is on Tuesday, and then I will create an assessment, and then you guys are going to scan and upload your homeworks to Blackboard, and then I'll grade them from there. Okay, now I'll save the rest of it for when we get down to just a little bit. So this is the homework schedule. The midterm is on July 2nd, and the final is on August 4th. These two dates don't slide. It will be on July 2nd. It will be on August 4th. So if you have family vacations or you're hoping to jump to Tahiti or something, just make sure you're not gone on these two days. Okay, any questions so far?
No, good.
Okay, jump this down here. Okay, so the midterm, you have 2 hours to complete. The final, you'll have 2 hours to complete. Okay, grading for this class. So we have homework, as I mentioned. The homework will be 20% of your grade. The midterm will be 40%. That's actually midterm. There's only one. And the final will be 40%. Okay, so for the exams are open, class assigned, textbook only. So again, you're going to be doing this in front of a webcam with Respondus. So you're going to show me your desktop and what's there. And what can be there is your textbook or a printed out version of your textbook. And a single page, 8.5 by 11 of notes will be allowed. The notes must be handwritten, no pictures, printed material, or examples allowed. It's basically just crib notes of, shorthand crib notes to kind of help you find things during the test. And again, no pre-worked out problems, no examples, and definitely no printed material. This note page that you're going to have, you're going to turn that in with your exam. Compromise tests will not be credited. So what we did last time is I actually created an exam through Respondus, and the exam has PDF sheets that have the problems, And then the exam has text boxes that you put in your answers. And I usually do 3 or 4 problems, and each problem has 1 or 2, 3 parts to it. So you give me the answers in the text box. But because of the nature of the way we do these things, your work is very, very valuable. So you have to be able to show me that you did the work, and then I have to be able to go into the work and give partial credit if any partial credit can be given. So what I also do, in addition to creating the exam that you take through Respondus, I also create an assignment that would be called midterm or final. And what you do is after you have finished your exam and submitted it, you take all of your handwritten notes or work that you've done for your test, along with your 1 page of notes, and you scan that stuff within 15, 20 minutes after your test, and you upload that onto Blackboard as an assignment. Does that make sense?
Yeah.
Okay, so this is the very beginning of the class. We have like 5 or 6 weeks before our first test. Please, please make sure long before the test is coming that you have access to a desktop or a laptop that has a sufficient Wi-Fi that you can reliably get on the system. The only problems I encountered last semester was when somebody had really spotty Wi-Fi connection and it disconnected during the test. Because if you're disconnected, you can't get back into it. That's how the system works. So once they were disconnected, they were done. And we had to figure out something to do there. So make sure you have good, reliable, it doesn't have to be Wi-Fi, you could have a landline or something like that, but just make sure you can get to the internet reliably with a laptop or a desktop, and you have to have a working webcam. That's part of the system. Okay, so please make sure everybody's set up to do that for the test. No makeup exams are allowed. We have to, basically exam security, we have to do it when we do it. Oh, both sides of the paper, okay for the notes. Yeah, if you want to, knock yourself out. If I don't tell you both sides, then what some people do is write basically microscopically to get it on one side. Both sides of the paper is fine. Okay, let's try to admit Raphael one more time here. Raphael, can you hear me? No, he can't. Okay, I give up. Okay. Okay, so homework is due on the date given by 5:05 p.m. Basically, the homework's due before class starts. So you're going to scan it and you're going to upload it into the Blackboard system. One thing of note, please, please, for my sanity, make sure that you scan it to PDF. JPEGs are horrible. And don't just take a photo of it with your iPhone and then upload it as a JPEG. I can't read that. It's nearly impossible to read it when it's like that. So make sure that you have some functionality that you can take your homework that you've done by hand and you can scan it to PDF. It is preferred that it's scanned all as one file, not 8 different files. And then once you have one PDF of all your homework, then you upload it to Blackboard. And then I will grade it through Blackboard. If you are late with the homework, you got sick or whatever, send me an email that says why it is you're going to be late, and then I will accept your homework for half credit. Homework, I still prefer that it's done on engineering paper, the good old-fashioned green paper that you buy in a pad, and it's just a lot easier to read that way. When you do your homework, please try to practice your professional lettering quality. In other words, make it readable. Make it so that somebody like me can open it up and read it and see where your answers are. It helps if you box your answers or put an arrow to your answer. But however you want to arrange your work. But please use the green engineering paper and complete it that way. I'm not too picky. You don't have to have a cover sheet. You don't have to have your student ID number. I know some professors are very picky about what you put on your homework. I just want it organized and so I can find what you're doing. Last comment about homework. Please use one sheet of paper per problem. Don't try to cram 5 problems onto one sheet. Makes it almost impossible to grade. And so that, without saying any more about the homework, but if I can't read it, I can't grade it. If I can't grade it, you don't get any credit. So please make it legible, neat, and easy to find the answers. Okay, so any questions on homework?
Professor, is the exams pretty reflective of the homework problem?
I believe they are, yes.
Okay.
Yes. And I really try to emphasize the homework because this type of class is the type of class where you can get it soaked into your head from these lectures, but you got to practice it. You really got to practice working these problems. It may make, so often it makes perfect sense when I do it, when I put it up on the screen and I walk you through it. It's like, oh yeah, that makes total sense. And then a week later, you try to do the homework and you're like, oh man, it takes practice. So the homework is really there to get you to practice it so that when you come in for the exam, you're better prepared for the exams. Okay, and then they have asked me to put on all of my syllabuses from now on that we do have tutoring services available. And you can contact these folks if you think that might be advantageous to you. The prereq for this class is CE 3501. Okay, so any questions at all about what we're doing? Okay, so that's the syllabus. If I change this, if I refine some of the scheduling down here at the bottom, then I'll repost this and let you guys know that it's been revised as we're moving along. But at least until the midterm, all of this is pretty set in stone. Okay, so that's the syllabus. I think the way we're going to do this class basically goes from 5 to 7. I think what we're going to do is like go from 5 to 6, and then I'm going to take like a 10-minute break, and then we'll find a convenient spot to break. But I'm going to try to work in a 10-minute break for 2 hours. 2 hours can be long if you just drank a lot of coffee or something. So does that sound good to everybody? A 10-minute break in the middle?
Yes.
Yeah.
That's fine.
Okay, great. Okay, and lecture number 1. I'm trying to think if I'm forgetting anything before we kind of dive into concrete design. Well, I'm going to interrupt myself if I remember anything else. Okay, so lecture number 1. Why are we here? We're here to learn concrete design. And today is just the fluffy, warm and fuzzy introduction before we really get into the good, interesting stuff. So starting as an introduction, we start with our materials. And our materials are concrete. Of the concrete, we have 4 basic materials: sand, or otherwise known as fines; aggregates, or coarse aggregate; water, of course; and cement. Those are the basic 4 ingredients of all concrete designs. And then in this modern day, we may or may not, but more often than not, we'll see some admixtures added in. Okay, so of the sand or fines, we have regular weight sand, which is by and large what most concrete designs will use, or you can have lightweight sand. In my career, I have never actually seen anybody use lightweight sand. Doesn't mean it's not out there and available, but we've never used it. Of your aggregates, you have regular weight aggregate and you have lightweight aggregate. The lightweight aggregate can be expanded, shale, clay, or slate. So these are manufactured products, or it could be pumice. Okay, so the expanded shale, clay, or slate is a manufactured product. It's a product made from these raw materials, and they run it through a process of they cook it in an oven, and it expands, and then it creates a rock that has voids in it. It's basically like a spongy rock. That rock does have less shear capacity than just regular natural rock. In other words, if you try to shear, it will shear through the rocks themselves easier than it would with regular weight. But there's pretty good advantages also to using the lightweight material. And namely, the weight of concrete is dramatically reduced. And we'll get into that a little bit later. Water and cement, together, these form what's known as a water-cement ratio. Did you have a question? Okay.
No.
Okay, if everybody's all right. So the water-cement ratio is a very important concrete design item. But this is for the mixed designs. And I want to be clear that this is just kind of background information right now. Mixed designs are different than concrete design. This course is really going to be about concrete design, not mixed designs. You may or may not have already had like a concrete lab where you guys talked about concrete designs or mixed designs. And that's where the water cement ratio comes in. So again, this is just background information. As a structural engineer, generally you're not going to be too concerned about how the concrete achieves the properties that you need. That's usually somebody else's problem, but this is how they do it. So the water cement ratio for a mixed design is key to achieving certain design strengths. The more water you put in, the less strength you're going to get out of that mix. So the water cement ratio directly affects the strength. So for example, you could have a mixed design with a water cement ratio of 0.5, 0.55, and my understanding is something with a water cement ratio in the 0.5, 0.55 range is really best used for something like sidewalks or slab on grade, or something where the strength really doesn't matter too much, because that's really about a 2500 psi mix. Not very strong, but really, really easy to pour. As opposed to water cement ratio in the realm of 0.4 is 0.4 to 0.45 is structural concrete, maybe 4000 psi, 3500 psi. When you get into the threes, 0.35, 0.33, now we're talking about real concrete, 5,000, 6,000 psi. And you really can't get too much lower than 0.3. Below that threshold, you actually don't even have enough water to fully hydrate the cement. So that's really kind of the extremes. It's 0.3, 0.35 on the high strength side, all the way to 0.5, 0.55 on the low strength side. Water cement ratio also affects workability. And so workability is closely related to slump. And as a structural engineer, you might say, workability and slump, not my problem. You make it work. You get it in the forms, but it could be your problem. If there is not enough slump, not enough workability, it's very difficult to pour the concrete into the forms and get good consolidation up to the forms and around all the reinforcement. So then you got problems. Then you got problems of rebar not fully developed because it's not adequately bonded, or you could have problems of honeycomb. When they pull the forms off, you got big giant rock cavities and craters in there. So it is important to the structural integrity of the member that you have good workability and good slump. Does everybody know what slump is? What does that measure?
Isn't that the cylinder test where they put the concrete in, then they flip it over, and then they see how much it goes down?
That is exactly right. Exactly right. They have a cone that they use at the job site. They fill the cone up with wet concrete. They flip it over onto a plywood piece of board or something, and then they pull the cone off, put it next to the pile of wet concrete that they have there, and measure how far from where it started it slumped down. How far did it go down? And so some general numbers, 4 inches is a low slump, pretty high strength, but low slump. Uh, 5 to 6 inches is kind of normal. I think you need about 6 inches to even pump concrete. And then 8 to 10 inches is more on the more workable side. I think people placing concrete love it when it's like 8 to 10 inches. That makes it really easy. More than 10 inches, I think you're pouring a sidewalk. And so that's the measure of slump. And the water cement ratio also will greatly affect shrinkage and creep. If you are pouring, say you're pouring a slab for a warehouse and you don't need a whole lot of strength, but if you get a lot of shrinkage, you're going to get a lot of cracking. So you might want to check that water cement ratio, not for the required strength, but just to put some control on shrinkage and creep. Okay, any questions so far? Okay, cement comes in 5 different types. These are ASTM specs for type 1 to 5. Type 1 is common all-purpose. Type 2 is lower heat of hydration and lower than type 1. And it also offers medium sulfate resistance. Sulfate resistance, that is basically a chemical attack. It is sulfates that are in the rock or in the aggregate or in the sand. And what will happen is those sulfates, when they mix it with the water, will cause problems down the line. They'll cause all kinds of micro cracking, and your concrete can literally just basically fall apart if it is susceptible to sulfate attack. Lots of great examples. You can walk around older structures. There's a lot of it in downtown LA. In fact, if you drive any of the freeways going into LA, especially around LAX, I've noticed it a lot. Concrete is just like falling apart. And really that was a sulfate attack over the last 30, 40 years since that was put in. And so all you can do for sulfate is try to source better rock or better sand, but a lot of times that's not economically feasible because you have to use what's close to you. So your other option is to get a cement that has some sulfate resistance to it. So that's another reason to use type 2. Type 3 is high early strength. That's something that we in the precast industry use extensively. because we need strength like in 10, 12, 14 hours, we need to get some strength so that we can release the product from the beds and start over for the next day. Job sites, there may be situations where that's important. There may be other situations where that's not so important. So it's a choice. And type 4 is low heat of hydration for large structures. Picture like the Hoover Dam, where that was a massive, massive structure. And even with a low water or a high water to cement ratio, it still generated tremendous amounts of heat from its own chemical reaction between the cement and the water. And that heat can actually get so hot that it's detrimental to the curing of the concrete, and you actually cook the concrete. So there's different ways to attack that. One of them is using type 4 low heat of hydration cement. And then type 5 is high sulfate resistance, the best sulfate resistance you can get. Any questions on cement type? Again, this is just background information. You as a structural designer designing concrete structures generally would not worry about this stuff. This is something that the contractor would worry about, because if this structure is susceptible to sulfate attack, it's their name that's on the line. The customer is going to come back and say, hey, you built this thing and it's fallen apart. It's the contractor's problem. But, the engineer should be aware of these issues as well. Okay, admixtures. Just about all mixed designs these days will benefit from admixtures. These are chemical solutions that you purchase and you mix into the concrete mixed designs, and they will alter the properties of the mixed design. They are either designed to alter the final structural properties, or they're there to alter the, as you're pouring it, workability type properties of the concrete. Air entraining admixtures are just what it sounds like. They entrain air into the concrete, creating millions and billions of teeny little bubbles. And mainly air entrainment is the best defense against water freeze thaw. So water penetrating the concrete, freezing, and then spalling the concrete. Not so much a problem around here, but in places where you have freeze thaw and de-icing salts and other de-icing chemicals, it really, really helps the durability of concrete in those regions. We have accelerating admixtures, again, to help with the strength or to get the strength earlier as needed. We have retarding admixtures. This might be for large pours. You may be pouring a matte foundation. I actually was fortunate enough to be able to visit a job site up in San Francisco when they were pouring the Moscone? I think it was Moscone Convention Center. And that matte foundation went from 6 to 12 feet thick. And it was kind of like a waffle pattern where it went from 6 to 12 feet thick. They had to pour that thing so thick because the water table is so high, they're worried about the whole structure floating away, literally. So they had to post-tension it down, and they had to make this giant matte foundation. So with a foundation that takes you 12 to 16 hours to pour, you may need some retarding admixtures to make sure that the first levels of the pour are not firing while you're still pouring more concrete on top of them. We have super plasticizers. These basically make, it's almost like oil. It's like an oily sheen that coats all the aggregates, and it makes a low slump concrete mix behave like a higher slump. It basically increases the slump without changing the water cement ratio. So you can go from a 3-inch slump to a 6-inch slump, which is totally doable without adding any more water, and still keep your high strength properties. And then we have some waterproofing materials that can be poured into the concrete. Concrete testing. Okay, so concrete is designed to a specific strength, F prime C. We're going to see this variable a lot in this course, F prime C. So F prime C is the value determined by you or me. That's what the structural engineer will determine and say, I need F prime C equal to, and we'll spit out a number, usually a nice round 4,000, 5,000, 6,000 PSI. But we, the engineers, specify F prime C, and we put that on the drawings. Somebody else has to design a mixed design that will achieve that F prime C, and then yet somebody else in the inspection or QC has to field verify that we're getting concrete that is at least equal to the value that we have called for in our design. So concrete is designed to a specific strength, 4,000, 6,000, 10,000, etc. And then the QC on site must do field concrete must be tested to comply with design strength with cylinders. So they'll take a number of cylinders, and there's an ASTM spec that says how many cylinders for how many cubic yards of concrete are being poured. ACI, American Concrete Institute, the ACI code recognizes 4x8 cylinders or 6x12 cylinders. To design a concrete mix, batch plants will mix trial batches. And trial batches are limited quantities. So generally, ACI 318 recognizes that if you have 30 tests, then you have enough data to base a design mix on. If you have less than 30 tests, then the requirements for passing the test go up because you have less data to justify it. But the standard is 30 tests, and each test is either 2 6x12s or 3 4x8 cylinders. So you need to create between 60 to 90 cylinders to verify a trial batch. Trial batches must average an F prime CR at or above the design strength. And so if your design strength that you're aiming for is less than or equal to 5,000 PSI, then your achieved average strength, F prime CR, has to equal the design strength F prime C plus 1.34 times S sub S. S sub S is the standard deviation of your data. Or F prime C plus 2.33, S sub S minus 500. If your concrete is high strength, over 5,000, then the criteria is F prime C plus 1.34 S sub S, or 0.9 F prime C plus 2.33 S sub S. So the site testing is acceptable if, okay, let me stop for a second, slow down for a second. So basically what I'm saying is, let me get my little spotlight here. This is the requirement of a batch plant. So say I'm Roberts Ready Mix or United Ready Mix or something like that, and I'm contracted to provide 4,000 PSI concrete. Well, I will design the mix, and then I will create 60 to 90 cylinders. I break all 60 to 90 cylinders, and the average of all those cylinders has to equal to or be above the lesser or the greater of these two. So whichever is the greater, I have to achieve that value or better in order for my mix design to qualify to be a 4,000 or 5,000 pound mix. Does that make sense?
So could you explain that again, please? Like,
sure. Somebody dropped out. There we are. Okay, absolutely. Okay, so again, you're the structural engineer. you say, I need 4,000 PSI concrete. And that's it. You put it on your drawings, F prime C equals 4,000. And that's all you do. The batch plant that is contracted to provide the concrete has to prove before the very first delivery truck shows up, they have to prove that this mix design that they've come up with will perform on the job. Because you can imagine how disastrous would it be to be pouring in a 70-story building and you're 30 floors off the ground and the concrete at the ground floor is not coming to strength. What a nightmare would that be? So we start that by saying, okay, this is the requirement for the people who are designing the mix design, that you have to achieve this strength in order for your mix design to qualify. And you have to qualify that with 30 tests of 2 or 3 cylinders. So 60 to 90 cylinders to verify this information.
Okay.
That makes sense?
Yeah.
Okay, great.
Sorry, so the average of the 60 to 90 cylinders strength has to equal the F prime CR?
F prime CR is the average of 60 to 90 tests.
Okay.
And so, okay, so let's throw some numbers out there. You as the designer say, I need 4,000 PSI. So the plant has crushed 60 6x12 cylinders, and the average of all 60 cylinders was 4,450 PSI. And you might say, well, 4,450 is more than 4,000. We're good to go, right? Not necessarily. The equation is, if 4,450 is what you got, but what you need is 4,000 plus 1.34 times your standard deviation. And if your standard deviation is large, that means your cylinders were all over the place. So if you had inconsistent results, if your cylinders were all over the place, then F prime CR very well may be 4,900 or 5,200. And your 4,450 wasn't good enough. You need to get better results. So that's how that works.
Okay, thanks.
Okay. Okay, so site testing now. Now we've moved from the batch plant, and the batch plant has their own quality control. Now we're talking about quality control at the job. Now the trucks are rolling up to the job site, they're pumping the concrete onto the building, and we're taking cylinders from the actual job concrete. Okay, so the cylinders that you take at the job site, if you average 3 breaks greater than F prime C, and you have no one break that is less than F prime C minus 500 for less than 5,000, or no one break less than 90% of F prime C for greater than 5,000, then you're okay. Your concrete has made the cut for the actual job site. And what happens if it doesn't? Does anybody know?
Don't they do like a
It's
mock
not
up
acceptable.
before?
So what happens is QC, the deputy inspection at the job site, will write up a non-conformance. That's what it's called. They write up a little ticket and says, hey, yeah, we're looking for 4,000, and you had 2 breaks that were under 4,000. We got a problem here. And then what they usually will do is say, okay, let's wait till 56 days and see if it comes up. And if it doesn't come up, now that this is pretty darn rare, thankfully, because of all this work that we did up here, this is pretty rare. But things happen. It does happen. You know, accidents happen. Somebody double dosed the water, double dosed the super plasticizer, or it sat in the truck in traffic too long. Things will happen. And so if you can't resolve the the low strength or non-conformance, then it goes back to the engineer of record. That goes back to you or I as a structural engineer and say, we got 3,800, you wanted 4,000, can you make it work? And then it has to go there.
Professor, if it reaches that point, would you, if it doesn't work, would you try to like retrofit it, or would you try to destroy, like take everything out and
Yeah, great question, great question. Now it kind of becomes into the realm of the engineer, and each engineer, each firm, if you will, would have their own policies on how to deal with it. And it really does become kind of job specific. Like in this case, I could justify it at 3,500, we're okay. Or in this case, this is really kind of hidden in an area of the building. Nobody's ever going to see this. Why don't we just pour some more concrete and thicken it up and make up for it? Or this is a very important architectural feature. You guys screwed it up. There's no way the architect's going to let you change it. Demo it out. Get rid of it. Sorry, I'm stalling here. Somebody sent me a question. And efficiency that comes out is higher. Oh, okay. Well, that was a question. And it's a good question. Okay, say it's the other way. I think this is what she's saying. If it's the other way, say like I as the engineer, I want 4,000 PSI concrete. And what actually gets broken on the job comes out to be 6,200. It's way higher than what I required. There's nothing in the code that says that is unacceptable. There's absolutely nothing in the code that says you can't overperform your concrete. You can, if you underperform, you may have a problem. But there's nothing that says that, even if I only wanted 4,000, then they deliver 10,000. Okay, fine. You guys probably spent too much money on your mixes because you put too much cement in it, but it doesn't, it is still acceptable structurally if it overperforms, but not if it underperforms. And then back to the destruction, I have actually seen it. I've only seen it once, but I have seen it. And it wasn't low strength concrete. It was very poorly placed concrete. There's a job in San Diego about 20 years ago where they were pouring a shear wall, and they poured the shear wall, they stripped the forms off. You could walk up to the wall and look right through the wall because there was a giant rock pocket about 10 feet long and about 12 inches high. It was just like a big giant seam of no concrete. And of course, the contractor went begging to the engineer record, please, 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 let us patch it. Can we grout it? Can we re-pour it? What can we do? And it was a shear wall. It's a structural wall for earthquake resistance. Engineer said, no, this is worse than I've ever seen. Tear it out. And they had to jackhammer out this entire wall, 2 feet thick, 40, 50 feet tall, 50 feet long. Had to tear it out. So it does happen. Okay, any other questions before I move on? Okay. And by the way, I know there are one or two, there may be some folks that are trying to add this class. Please stick with me, and we'll talk about that towards the end of the lecture, but I haven't forgot about you. So this is starting a whole new section. You guys want to take a 10, and let's reconvene at 6:10. Is that okay with everybody?
Yes.
Sure.
Sounds good.
Professor, I have a question.
Yes.
Just to clarify, on the site testing, acceptable if where it says f prime of c is less than or equal to 5,000 psi, and then it says no one break. Is that referring that there's no breaks under that psi?
Okay, let me clarify. For every set amount of yardage that you pour, I'm not sure what the number is, 50, 75, but say it's like, say, every 75 cubic yards of concrete that you pour, you have to take 3 cylinders. And you break those 3 cylinders and you record what those results were. Say that, again, you want 4,000 PSI concrete. Say that you want 4,000 and you got 42, 48, and 43. No problem. All 3 breaks are above 4,000, no issue. They write it in the report. But let's say that you had 38, 42, 46. The average of 38, 42, and 46 is still over 4,000. So we're okay with the average. But that one break was 38. That one break is still higher than 4,000 minus 500, which is 3,500. So if the average is better than F prime C, and you didn't have no one single break less than F prime C minus 500, then it is acceptable. Let's take another example. Say that you took your 3 breaks and you got 32, 48, and 53. That tells me something's wrong. If you got 32, 48, and 53, that is so across the board. The average of 32, 48, and 53 may still be over 4,000, but you had that one break that's less than 3,500, 32 being less than 35, it is not acceptable, and that would be a nonconformance. Does that clarify?
Yeah, thank you.
Okay, great. All right, let's take a break and let's reconvene at 6:10. Okay, hopefully everybody's back. And so let's get rolling here again. So now what we're going to pick up here is we're going to talk about concrete stress strain curves and how the different flavors of concrete look on this. So you probably remember this, hopefully remember this from your mechanics of materials, where we did stress and strain, and it's very useful for looking at the behavior of materials. So if I start with a fairly low strength concrete, relatively, so an F prime C 3000 PSI, it peaks, as you can see, about 0.002 is your maximum strength on this, but it will strain out pretty darn far before it actually crushes. So at 3000 PSI, concrete is somewhat softer, and it actually is a bit more ductile, but it's much lower strength. You can see the trend here is if I go to 4000 PSI, again, I'm kind of peaking out at about 0.002 inch per inch, but it's dropping off a little quicker now. And 5,000 and 6,000. So you can see the trend is that the higher the strength the concrete is, the less strain it is available to you. So there are actually some downsides to using some really high strength concrete. 8 or 9 or 10,000 PSI concrete may not be as ductile as some of these softer concretes. Also, what is the note here is the 003. This is going to become an important parameter down the line. ACI 318 is going to limit our usable strain to 003. Even since some of these softer concretes can go way beyond 003, that is the one limit chosen by ACI to apply to all concrete. And you can see at 002 is where most of our concretes kind of peak. These are loosely defined, but we generally will accept that the elastic range for concrete is up to about 40% of its strength. This is where the line is pretty straight, and we can solve for serviceability issues, deflections and cracking and stresses, things like that. As long as we're in the elastic range, then moments of inertia and Young's modulus of elasticity are all valid in this range. Beyond that is what we call the plastic range. And the plastic range is just that. The concrete is not acting in a linear fashion. It's acting in a nonlinear fashion. Epsilon sub naught is how we pronounce this little guy, or that's how I say it. Epsilon sub naught is taken to be about 0.002 for all these strengths. That is where the concrete peaks. And like I said, the assumed maximum strain, epsilon sub c, is dictated by ACI code, is 0.003. And this actually can vary a little bit. The Canadian code and the European code, I think they'll let you go up to 0.035. It doesn't really make any difference at all. It barely changes any of the answers. So it's kind of arbitrary, but it works at 003. And again, throughout this course, I am going to be citing to you chapter and verse where you can find these things in the ACI code. So ACI 318, and you can find it chapter 22 and 0.221. Oh, which types of cements behave? Do all 4 types? Yeah, all 5 types. All 5 types really don't change this behavior at all. The 5 types have those other properties that we talked about. And if it's high early strength, then what's not shown on this graph is how many days did it take to get to this strength. But high early strength will get to this strength earlier. Retarded concrete will get to this strength later. But after 28 to 56 days, it doesn't really matter anymore. When you put this in an actual compression testing machine and squash that cylinder down, what you're doing is you're measuring the stress with the strain. And so this would be like a test representative of one day. This is all one test. And you tested it from 0, it went up, 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 then it started dropping, 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 and it crushed. Okay, any other questions so far? Okay. We have a indicator, modulus, or excuse me, we have the moment of inertia and we have the modulus of elasticity. The modulus of elasticity is actually the secant modulus of elasticity. So that's kind of the tangent to the very beginning of this curve here. And ACI defines that as the density of concrete in pounds per cubic foot to the 1.533 square root F prime C. And this is applicable for all concrete densities, where WC is the density of concrete in pounds per cubic foot. Or we can use the simplified equation for normal weight concrete only, where all of this is just combined to be 57,000 square root F prime C. Young's modulus, E sub C, is valid only in the elastic range. A quick note. We're going to see square root F prime C over and over and over in this course. It's an indicator for many different things that we are designing to, like at what stress will the concrete rupture or crack? At what stress will the concrete fail and shear? It's a very valuable tool. But the problem, and I just want to put this out right up front, is that F prime C is usually PSI, but you can't take the square root of PSI, that's pounds per square foot. So anytime you see the square root of F prime C, first of all, the number you put in here has to be PSI, always. You cannot use KSI. The square root of 4 KSI is not the same as the square root of 4,000 PSI. Mathematically, you can't just take the answer and then multiply times 1,000. It's not the same answer. So anytime you see the square root F prime C, always, always, always put for the PSI F prime C in here. And then the units that come out of this is PSI. So this is going to say, this is going to be 57,000 times the square root of 4,000, say. That answer will be PSI. And to go from PSI to KSI, you just then divide by 1,000. But when it's 57,000, this is PSI. Okay, does that make sense to everybody?
Professor, you said to go from PSI to PSF, you divide by 1,000, or is it the opposite way?
To go from PSI to KSI, divide by 1,000.
Okay, divide. Okay.
Yeah. So if I guess I should back up a second, just make sure everybody's on the same page. Is everybody familiar with a kip? A kip is a very common designation of force in the structural engineering world. So a kip is 1,000 pounds or a kilopound, yes. Okay, so that means that KSI is kips per square inch. And so 1 KSI is equal to 1,000 PSI. And we're going to use those units back and forth like a billion times in this class, or a million K times, whatever. Anyway, so Young's modulus, valid only in the elastic range. It is used for serviceability checks, deflections, and cracking. Concrete strength, designed based on the plastic range of concrete stress. Okay, creep and shrinkage. Creep and shrinkage is a property of concrete and water. Creep and shrinkage are both the expulsion of water from the cement matrix. So you poured the concrete, you had a lot more water in your mix than you actually need for the hydration of cement. You need a lot more in there for workability and to get it into the forms and vibrate and consolidate and all that. So there's extra water in the concrete mix as it's curing. Well, that extra water is going to want to come out, and it comes out over time. So the expulsion of water from the concrete mix starts off rather dramatic, and then eventually over time descends to basically no more at all. So like a horizontal asymptote. And this is for both shrinkage and creep. So shrinkage is the expulsion of water over time with no other factors involved. You pour the concrete, there it is, and over time, water is going to come out of that concrete into the atmosphere. And it creates a reduction in volume. The concrete will shrink because you're losing the water, a volume of water, you're losing it to the atmosphere. So the concrete itself actually will shrink. And most concrete is restrained in some way. So as it's trying to shrink itself, something is going to try to restrain it from shrinking, and it's going to crack. So I'll just say it right up front, so nobody's surprised. All concrete cracks. All concrete structures crack. Cracks are not evil. They're not the end of the world. All concrete will crack. What we do in our jobs is we control the cracking, okay? So think of it like a slab on grade. Think of like pouring a patio or pouring the concrete in your garage. When you pour that concrete, you pour it up to the forms to a certain size. We do everything we can to slow the shrinkage down. We cover it with plastic, or we soak it in water. We do whatever we can to slow down the shrinkage. But inevitably, water is going to come out of that concrete into the atmosphere, and that slab is going to shrink. Now, that slab is not free to just shrink as much as it wants. There's friction between it and the ground. Or it may be tied into walls, or it may be in some way restrained. And that's where you get cracking in your floor slab. Okay, so what's the difference between shrinkage and creep? Is there a difference? Well, creep is the same thing. Creep is the expulsion of water, but we separate the same phenomena, we separate it into two, shrinkage and creep. And we call the part of the reduction in volume of concrete because you're squeezing it under stress, we call that creep. And the part of the reduction in volume of the concrete that is not being squeezed, that's shrinkage. So it's really the same thing. We just break it up into two components so that we can get our hands around it and call it something. So creep is the expulsion of water under constant stress. Creep causes an increase of strain under constant stress. That's the key. right there. So if you think back to the stress strain diagram that I just showed you for the various concretes, you can stress a concrete up to 2,000, 3,000 psi, and it causes a strain. Every stress causes strain, and so you may cause the concrete to strain. And so what happens? If it's a beam, it deflects. If it's a column, it squishes down. But creep keeps it deflecting, and it deflects a lot more in the first weeks and months, and then it just keeps on deflecting over a period of several years until the increase in deflection due to creep over, say, maybe 3 to 5 years is barely noticeable anymore. But it will cause a beam that maybe has a 1/2 inch deflection the day you kick the forms out, and then you come back and you revisit it in 3 to 4 years, and that 1/2 inch deflection, oh my, now it's 2.5 inches of deflection. That can happen from creep, and it's something that we have to keep in mind. Any questions on creep and shrinkage?
Professor, do we combat that by using pre-stressed concrete?
We can. That's one way to combat that. If you're having too much deflection, you can use pre-stressing. You can also specify higher strength concrete that has a lower water to cement ratio, and you'll get less creep. And additionally, we also have some other tricks where we can put some steel in there to help control that as well. As I said, creep and shrinkage are most profound in days and weeks after casting, but will continue for years. Okay, concrete tensile strength. In concrete design, compression is positive, tension is negative. Okay, this is the first big, oh my gosh, what are you doing to me? I know, because I just taught it, that mechanics of materials is the exact opposite. Tension is compression, or tension is positive, compression is negative in mechanics of material classes. In concrete design, it is the opposite. So if you have 3,000 psi stress in your concrete, that's compression. If you have minus 400 psi, that's tension. Okay, so everybody straight up on that?
Professor, why does the change happen? Like,
Why? Why did we do this to you?
yes.
Why are we so evil? It's tradition.
Okay.
It's really nothing more than just tradition. Reinforced concrete design has been around over 100 and something years now. And just the tradition has been that we design the concrete to take compression and we design the steel to take tension. That's how the two materials work beautifully together. Concrete is great in compression, steel is great in tension. So we're always designing concrete for compression. We're always designing steel, almost always designing steel for tension. So those are the positives. We don't want to work with negative numbers all the time.
Right.
So
Okay.
I think that's why. Okay, but I want to make sure everybody's clear. Throw out what you just learned in mechanics of materials. This is going to be our sign convention. So again, here's my concrete, 3,000 psi, 4,000, 5,000. These are positive because this is compression. And this is positive because this is compressive strain. But what I've done here is I've added negative stress and negative strain off to the left right here, this little tail. And this little tail is the portion of the concrete that can actually take tension. Concrete can take some tension, but then it cracks. So there's a limit of how much tension it can take until the concrete cracks. And that is F sub R. So F sub R is known as the modulus of rupture, and it's generally taken as minus 7.5 lambda square root F prime C. It's minus because concrete in tension is negative. Lambda is a factor less than 1 to account for lightweight concrete. And F prime C, like I said, F prime C goes in here. And then epsilon sub R is the modulus of rupture, occurs at epsilon sub R, which is the modulus of rupture F sub R divided by Young's modulus. And it generally is anywhere from 0.00009 to 0.015. Okay, I got a question explaining modulus of rupture again. Okay, so picture this. If I have a cylinder of concrete, one that was made for crushing, one you're going to compress it until it crushes. But say I could take that cylinder of concrete and I could pull it apart. I could put it in tension. Well, that cylinder of concrete is not going to just instantly crack and fall into two pieces. It's going to take some force before it separates at a crack. In other words, you could not hold a 4x8 cylinder in your hands and pull it apart. Well, at least I've tried it. I can't do it. So there's some strength in the concrete in tension. And that limit is the modulus of rupture. If I have less than this number of negative tensile stress, then the concrete won't crack. If I exceed this number, then the concrete has cracked. Does that make sense? Okay, they still have that? Yeah, but not exactly. It's not the force, it's not the strength, it's the stress. And remember that stress is, force is stress times area. I'll be super clear. I know I'm being picky, but it's going to come back and bite you later if we're not clear about this. Stress and force are totally different. One is pounds, one is pounds per square inch. So a force times area, or a stress times area, is equal to a force. So if you take a cylinder of concrete and you try to pull it apart, you're putting a tensile stress in there, and it can only take so much stress until you exceed the modulus of rupture. Modulus of rupture is a measure of stress. And when you exceed that, it will crack and fall into two pieces. I'll get to lambda in a second. I will elaborate on lambda. Okay, concrete shear strength. Actual shear strength is very difficult to measure in concrete. Actual shear strength does not control design. Concrete is weaker in diagonal tension than shear and will fail in tension first. So anytime somebody says the concrete failed in shear, it didn't actually fail in shear. And we'll get to that in much more detail when we get to shear design, but just a property of concrete hardly ever actually fails in shear. Okay, the lightweight concrete shear factor, lambda. And I give you, again, you're going to see this over and over and over, a section where you can find this in the ACI code. If the density of the concrete is, if it's all lightweight, and this is a term used by ACI, all lightweight concrete refers to lightweight sand and lightweight aggregates. It generally has a density less than 110 pounds a cubic foot, and lambda will be 0.75. If it is sand lightweight concrete, and I know you would think like, wait a minute, lightweight sand? No. What this means is regular weight sand, lightweight aggregate. So sand lightweight concrete is regular sand, lightweight aggregate, and it is actually what most people are referring to when they say lightweight concrete. So sand lightweight concrete is anywhere from 115 to 125 pounds a cubic foot. and lambda is 0.85. And then you have normal weight concrete, normal sand, normal rock. The weight is usually 145 to 155, depending on the density of your rock, and lambda is 1.0. So if you have normal weight concrete, lambda just becomes 1 and kind of goes away. Linear interpolation can be used between the classes. Okay, everybody good on concrete? Okay. Yes, do I have a question?
Nope, just saying I was good. Sorry.
Okay. All right, so let's move to the reinforcing steel. This is the other half of the beautiful partnership between steel and concrete, that is reinforced concrete. Reinforcing steel. It is manufactured under a specification covered by the American Society of Materials and Testing, and I'm not going to spell that out again. It's always just ASTM. And so we have these different flavors. We have ASTM A615 rebar. It comes in grades 40, 60, 75, and 80. And it is known as plain carbon steel. There was a time when grade 40 was the norm and grade 60 was the high strength stuff. Boy, that stuff's expensive. Yeah, it was about 30, 40 years ago. Then there was a time when you could still get 40, but you could get 60 pretty regularly. That's pretty much when I started this whole game. Now, 75 is almost impossible to get. 60 is the norm. 80 is pretty easy to find. And you know where is the only place that I looked? I tried to find grade 40. Do you know where is the only place that I found grade 40? Anybody take a guess?
Home Depot,
Oh my gosh, how did you know that?
the ready mix concrete.
Home Depot is the only place on the planet that still sells grade 40. And I asked them, why? Why do you have grade 40? You know what the answer was? This blew my mind. The answer was because people will build swimming pools. And when you build a swimming pool, you got to line the pool with concrete. And that concrete has to be reinforced. So the people who build swimming pools, grade 60 is too hard to put the rebar into the hitch of their truck and bend it by hand into the shape they need for the wall of a swimming pool. So they want grade 40 because it's easier to bend by hand. And that's it. That is the only use of grade 40 left in the world. Then we have A706 steel. A706 comes in grade 60 and 80. It is known as low alloy steel. When I started this crazy game, pretty much all the steel out there was A615 grade 60. And if you wanted A706, you had to pay extra. And the reason was that A706 is a alloy low carbon steel, which means they're able to take some carbon out and put other alloys in like molybdenum, manganese, chromium, nickel, other alloys go into it, and it makes it weldable. So not that A615 you can't weld it, but you got to be a lot more careful welding A615. A706 was first released to the industry as a rebar that you can weld a lot easier because the carbon is much lower. So that's A706 used to be called A706W for weldable. And you would buy it and you pay extra just to get that weldable rebar. Not so much anymore. Nowadays, rebar is not made from just raw iron anymore, like in the old days. Today, and I got a really neat trip one time. I got the I was very fortunate to do some work for what used to be Tamco over in Rancho Cucamonga. That's a steel rebar rolling mill. And so doing the work for them, I got to visit. And they showed me how we make rebar in this day and age. And rebar today is, for the most part, made out of scrap steel. So they had this pile of shredded steel, like mountains of the stuff, that are washing machines and bicycles and automobiles and just anything made out of iron goes into this heap. And what they told me was they grabbed their metal from this giant pile of steel, melted in this cauldron that's about the size of my condo building. And when they melt it all down, all the other stuff that's already in the scrap is the alloying that they need to roll A706. They don't have to do anything other than just sprinkling a little bit of pixie dust to make this stuff A706. So what that means is nobody's rolling A615 anymore. It's almost all A706. So that's what I know about A706. 80 grade is fairly new, but it is in the specification now. It is in the code. ACI 318 now, it's in the code for grade 80. And I understand 100 is coming soon. We also have this stuff called A955. It comes in grade 60, 75, and 80, and it is stainless steel. This stuff, in my career, I've seen it used maybe twice. You might as well be welding pure gold ingots inside of concrete. This stuff is so expensive. There's almost always a better way to do it than to use stainless steel. But there are certain applications where stainless steel is what is specified and you have to use it. So this is the spec and these are the yields that are available to you for using stainless steel.
Professor, why did they use it in those two cases?
The one that I
It's so
remember
expensive.
specifically was for, we made a double T. It's a precast double T, so it's like a floor member. It was being used as a bridge, and it was being used at the Hyperion wastewater treatment plant for Los Angeles. And if anybody knows what Hyperion, what they do there, that is some nasty stuff. That is some very, very nasty, caustic stuff. And just about any concrete that they put into this facility destroys itself in 5 years. So they wanted to try to use precast because precast concrete generally will have higher quality than site cast concrete. And they made us use stainless steel for everything. I've never gotten a call back, and that was about 20 years ago, so I assume it's still there, but that's why we use stainless.
Thank you.
And we have this new stuff, this newfangled technology. It's called A1035, and it only comes in grades 100 and 120. And this is actually a chromium alloy steel. This is some super high strength stuff. But one, you can't weld it. You just get all kinds of underbead cracking if you try to weld grade 100, 120 chromium steel. The other problem with this is that ACI is a few years behind. And so there's really not a lot of applications that you can use. ACI will limit the allowable yield that you can use. So you can buy 120, and the code says you can only design to 80. So there's really no point yet, but we're getting there. We will get there. Okay, here is a stress strain diagram for a typical rebar. So when I say typical rebar, I'm saying A706 grade 60. So if you actually did a tension test of a stick of rebar, you monitor the stress, you monitor the strain, which they do. You can do that down at down at the testing. I'm sorry, I get distracted. You go to a testing lab and they can pull a coupon of rebar, and this is what you'll get. What kind of steel is A992 grade 50? That is, I think that's structural steel, like wide flanges. So that would not be in this conversation. Okay, sorry, ADD here, get distracted. This is very typical of what you might see for a real rebar test. The minimum specified for 60 KSI is here. This is 60 KSI. This particular might yield at 72 KSI, which is perfectly fine. As long as it yields at or above the specified 60, then it meets the criteria for the rebar. And so this is what it might really look like. The red line is how we're going to design it. So for our design purposes, we're going to simplify this. We're going to call from 0 to the yielding strain the elastic range, where you can determine what the stress is in the rebar using Hooke's law. Hooke's law is that the strain times Young's modulus is equal to the stress. So we can use that relationship to solve for the stress in this range. But if you're in the yielding range, then the stress is just assumed to be the yield stress, or 60 KSI in this case. And then we have the strain hardening range, where the steel gets tired of just yielding and puts up its last fight and gains more strength. Strain hardening, for the most part in concrete design, is ignored. It's conservative, but we're just going to ignore it altogether. And we're just going to assume that our rebar yields forever. And it's the strain in the steel will never be your limiting value. It will always be the concrete that's going to fail first. Okay? So this is kind of the real behavior, and the red line is what we're going to assume. Epsilon sub y is the strain at the yield. F sub y is the stress at yield. And E sub s is Young's modulus for steel. Okay, I think what I did here is I'm going to say in writing what I just said. Blue line represents the possible actual rebar stress strain curve. Real curves can vary significantly from this ideal. That's another reason why we don't use this curve. Different rebars of the same ASTM spec have very different curves. They all yield at least 60 or above, but the shape of the curve can be very different. The red line represents the bilinear assumption that we're going to use for concrete design. Consists of two segments, the elastic portion up to the yielding strain, epsilon y, and the flat yielding portion from epsilon y to an infinite strain. Again, we don't put a limit on the strain for steel because we know it's not going to be what that's not what's going to fail. The concrete will always fail first. Epsilon s is taken to be 29,000 KSI, and this is for all grades of rebar. The yielding strain, this is Hooke's law, so the yielding strain is equal to the specified yielding stress divided by Young's modulus. And for grade 60 rebar, if you plug 60 here, 29,000 here, you get 0.00207 inch for inch. And that's going to be a very typical value that we're going to use for this class. Although ACI 318.14, hereafter referred to as the code, so I'm just going to say ACI 318, or I'll just say the code, does not prohibit using various grades of rebar, it does limit the design value used. Okay, so here's why you should have, hopefully as soon as you can, a copy of ACI 318.14, because I'm going to say many times, okay, the table 20.2.2.4a on page 329, right? And we could all turn to that page and look at that table. That table prescribes what yield stress may be used in various conditions. Higher grades may be detailed, but the design is limited to the grades from the table. For example, you may specify shear ties in a beam, and you say, okay, I want those to be A706 grade 80. Fine, they'll provide you with grade 80 ties, no problem. But this table says in your calculations for the strength of that beam and shear, you can't use anything higher than 60. So even though it may actually be 80 or 100 for that matter, you can't design any higher than what this table says you can design to. And it's a fairly complicated table, so I couldn't reproduce it in this presentation. Okay? And another good reason why everybody needs to have the code so that we can look at these things as we're going through these slides. Reinforcing steel, hereafter referred to as rebar. I happen to be on the AWS, American Welding Society, D14 Code Committee. That's one of the other things I do as a hobby. And that is the Rebar Welding Committee. We've got people on there that are so picky, and they will, if you even say, yeah, we're going to weld the rebar. No, 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 no. That's reinforcing steel. Give it up, dude. It's rebar. So I try to be specific, and then I'll have little things like this to say, it's not necessarily slang, but most of us call it rebar, even though technically it's reinforcing steel. Anyway, rebar sizes are standardized. Every mill has their own molds for casting rebar, and a number 11 bar from Tamco will not look exactly like a number 11 bar rolled out of Cascade, but they have some properties that are standardized. One of them is the diameter, and the other is area, and a third actually is the weight. So the sizes can be found on page 1.1, table 1.1 on page 25 of the text, as well as Appendix A on page 507 of the code. And I produced them here. So they're also in this presentation. This presentation, along with all my other presentations, was uploaded to Blackboard. So you can download this and use this as a reference as well. But from here on after, I'm not going to spend a lot of time on telling you why a number 8 bar has an effective area of 0.79, why a number 4 bar is 0.2. You're going to see in the calculations to follow, when we actually really start getting into this, I'm going to say 8 number 8s, and I'm just going to say 8 times 0.79 inches squared. Where did I get that number? I got it from here, I got it from page 25 of the textbook, or I got it from page 507 of the code, okay? Also, there are a lot of tables that make some of these calculations. Once you get the hang of doing the calculations, there are shortcuts. I would suggest you do them the longhand way first, but then as you do them repetitively, you can start using the tables in the back of your textbook as shortcuts. But you can't do that if you don't have the textbook. So please, please, please make sure you get a copy of that textbook so that those tables are available to you. So that is the end of my light and fluffy, warm, fuzzy presentation for today. For those of you who are trying to add, please stick around for a few more minutes, but we do still have another 10 minutes here, and I can answer any questions.
Oh, Professor, will you be giving us the link for the YouTube?
Yes. What I tried to do last semester at first is as soon as I finish the Zoom session, it records it and saves it on my computer. And then what I was doing is I was uploading them to Blackboard. Well, I did that about 4 times, and then Blackboard said, "Hey, sorry, pal, you're out of memory." And then it was just screwed up from there on out. I can never get that memory back. So this time I learned. I will be uploading them to YouTube, not tonight, hopefully tomorrow. And then once I do that, they give you like a little link or a code, and I will put that code into an announcement on Blackboard. If you don't get the code, or you can't use the code, or for whatever reason, there's some problem, what you can always do, and just as common knowledge, you can go to YouTube, type in my name, Aaron Pratt, and some stuff will come up. There are, of course, more than one Aaron Pratt in this world who have put videos on YouTube, but type in Aaron Pratt, put in a keyword like concrete or 4501, something like that, and videos will come up. I'll tell you right now what you're going to find. You're going to find the videos that I upload for this concrete class. You're going to find the videos that I uploaded for the mechanics of materials class that we just finished a few weeks ago. And you're going to find some videos from my off-roading club from about 4 or 5 years ago. You can watch those if you're morbidly curious about crawling trucks over rocks, but for the most part, just look for the concrete stuff.
Sounds good. Thank you.
Okay. Any other questions on anything today on this introduction to concrete? Also, please keep an eye out. It is my intention that Tuesday or before Tuesday, I will put up what the first homework assignment is. And from a week from Tuesday will be when the first homework is due, and every Tuesday thereafter. Anybody else?
Professor, when we begin to do examples, are you gonna kind of just run through it like verbally, or are you actually going to write stuff as you speak, or how is it gonna work with examples?
Okay, that's a good question. They are all pre-worked out on the PowerPoint presentation. And I am not a power user of PowerPoint by any means, but what you're going to see, just to make it a little bit more doable, is when I go through examples, I go through them line by line, like this. And I will talk you through them. But I found that if I just throw the whole example up there, everybody's eyes glaze over and like, okay, that looks easy. But I'm going to go through them line by line. The tool that we have here for annotation, I'll show you the example. If somebody has a question, then this is my tool for answering anybody's questions. And this tool is awful at best. I can barely even write my own name, as you can see. So I am going to try to do most of everything is pre-written out for the reasons that I'm showing. And I'm going to use this little spotlight to kind of show you what I'm doing. And I'm going to walk you through examples in this fashion. Please don't let that stop you from asking questions. And if I feel that the question needs some kind of a diagram, or I need to point to something or draw something, I'll do my best with this tool. But this is how we're going to go through them. And then all the PowerPoints will be uploaded to Blackboard. So you can peruse them at your own leisure anytime if you want to go back through examples line by line. And of course, this is being recorded, so you can listen to me jabber about as I'm going through the examples as well. But when we're in a classroom on a whiteboard, I would do this with a pen, and I would be talking to you as I'm writing with a pen, and I'd be looking at each one of you in the eyes, and I know who's asleep, I know who's paying attention, and I know who's completely, utterly, hopelessly lost. And I could use those tools to elaborate and clarify in the classroom. I can't do that here. And you can probably tell it's frustrating that I can't do what I normally do as a teacher in this format. So this is the best we have.
Sounds good. Thank you.
Okay. Any other questions for me? Okay, if not, good session, good first session, hopefully. And if I can just have whoever's trying to add my class stick around for a minute or so. To everybody else, thank you very much for indulging me, and we will see you on Tuesday.
Thank you, Professor.
Thank you.
Have a good weekend.
You too. Thank you.
Thank you, Professor.